Hello everyone, and welcome to the very last new material of AP Physics C Mechanics. So this is really a type of problem that we've done in other ways throughout the year, but this is a special circumstance, and it's one that requires quite a bit more math and specifically quite a bit more calculus. So I'm going to go through this in detail. If you have the worksheet that's associated with this PowerPoint, then the very first problem on the worksheet is the problem that you see here on the screen. And we're going to kind of work through it together, and so you can take notes right on the worksheet. So, as you can see here, you've got a car, and the car is moving to the right, right, with a particular velocity. We've done problems like this, but the difference here is when we get to this part, where the car encounters a resistance force equal to negative kV, where v is the velocity of the car, and k is just a constant. So this is a resistance force, whatever it is, that is dependent on the car's velocity. Now this is different. Right? When we've done problems like this, motion type things, and done it with forces, our resistance forces, most notably sliding friction of surfaces rubbing against one another, is always constant. Right? And so we can deal with it as a constant force, which results in uniform accelerations and kinematic equations and all that good stuff. But here we have a problem where as your car speeds up or slows down, the resistance force is going to change. And if the resistance force changes, then your net force changes. And if your net force changes, then your acceleration changes. And if your acceleration changes, then we can't use kinematic equations and we need more complex math. So let's go through the problem here. This is actually a problem from 1993. Problems like this one show up pretty much every 2 to 3 years on the test. Will it show up this year? Who knows? But I'm going to try to prepare you for it. Just kind of hang tight with the math here. Right? And of course you can slow this down and stop it and go back and take notes and all those things as we work. So we're going to start out by drawing a force diagram for this car, as we normally do. So the forces that act would, of course, be a downward force of gravity and an upward normal force, a support force from the road on the car. Now, of course, those forces would be, that's right, they would be the same size because this car is not accelerating vertically. Now, if you read the problem here, it says that there's a constant force FO applied to the car. Right? So since the car is moving to the right, I'm going to draw that force FO to the right. Don't really know how big it is. Doesn't really matter at this point. And then there's this resistance force, right? Negative kV. Right? They made it negative because the car is moving to the right, which is positive. So resistance forces are going to act backwards. Now that force is going to change depending on what the velocity of the car is. So there could be cases when it's less than F of O, it could be more than F of O, it could be equal to F of O. We're just going to have to play it by ear as we go. In this case, they're not really looking for you to be all that specific about sizes. They would give you points for each one of these forces, properly drawn, properly labeled. Now comes the math part. So now we're going to figure out the horizontal acceleration of the car, and we can only write it in terms of K, V, FO, and M. Nothing super complex here, just like we've always done, right? We're going to figure out the acceleration by doing Newton's second law. Net force is mass times acceleration. If we go back to our force diagram, right, you'll notice that horizontally we've got F of O pointing to the right, and we've got the resistance force pointing to the left. So that would make it F of O minus kV equals mass times acceleration. And yeah, you could put this in as the resistance force, but we need our answer in terms of K and V anyway. Right? And this minus sign, well, it comes both from the equation for the force and from the fact that the way we drew the diagram, it was pointing to the left. One step of algebra, and there's your answer. This was really, I think, a couple of points in 1993. No fancy math there. We've done that lots of times. Right? It's just that traditionally when we've done this, this has been some constant force of friction. Now, here's the hard part. They want to know an equation for the velocity of the car as a function of time. It's got to be in terms of k, f, o, and m. Okay, the velocity of the car is a function of time. Well, this is what we just figured out. We figured out the acceleration. So how do you find the velocity when given an acceleration? Hopefully you're thinking, oh, I know how to do that. I take the integral. But we have a problem. And the problem is that the velocity is itself a function of time, an unknown function of time at this point. Right? So we have a tricky little integral that we're going to take here. So I'm going to start out by writing this as something called the differential equation, which means an equation that has a derivative inside of it. I'm going to plug in for the acceleration what we know it is in calculus. Right? We know the acceleration is the derivative of the velocity with respect to time. This, by the way, is known as a separable first-order differential equation. Separable refers to the technique I'm going to show you on how to solve this kind of problem. First order means that it's just a v, there's no squareds or square roots or anything. And differential equation because it has a derivative in it. They actually use this language sometimes in the AP test where they'll say write a differential equation for something, and what they mean is you write it with the derivative inside of it. Now, how are we going to solve this? Well, we're going to use this a method called separation. All right, we're going to separate these dv and dt from one another, and we're going to try to gather up everything that has a v in it on one side and everything else on the other side, like so. Check the algebra, right? I moved this down to the bottom over here, and I moved this over to the top up here. And now we're going to take the integral of both sides. That's legal, right? We're doing the same thing to both sides of the equation. This side is relatively straightforward. We could probably do that one right away, but this side is more complex. We're going to have to do something here that you've hopefully learned about in calculus by this point, which is called u substitution. So we're going to let a dummy variable, we're going to call u for now, be equal to f of o minus kv. And then we're going to take a derivative of this function with respect to our variable, which is v. Right? F of o and k are constants. So if we take the derivative of this with respect to v, f of o is a constant, so the derivative of it with respect to anything is 0. The derivative of negative kv with respect to v is just negative k. One little step of algebra, right? dv is the negative du over k. And we can plug that in right over here. And we can plug in u for f of o minus kv. So I'm going to do two substitutions. U is going to get substituted in here, and negative du over k is going to get substituted in here. Note on the right-hand side, I factored out the 1 over m, the 1 over the mass of the car, because it's a constant, and I can do that. So make sure you're okay with my little u substitution here. Okay, so we substituted in u right here, right? Here it is. And then we substituted in for dv, negative du over k. So first thing I'm going to do is I'm going to move all the constants over to one side just to make our life a little easier. So notice I multiply both sides by the negative, and I multiply both sides by k, and I move it over here. And now we're ready to take the integral of both sides. Well, on the right-hand side, it's a fairly simple integral. The integral of, essentially, there's a 1 here with respect to t, is just t. Right, so no big deal there. The left-hand side gets a little tricky. We've got the integral of 1 over u du. Hopefully you've had enough calc by now that you know that this is a problem, because 1 over u can be written as u to the negative first, and if we use the power rule and we take our integral, add 1 to the exponent, divide by the new exponent, well, negative 1 plus 1 is 0, and you can't divide by 0. So hopefully in calc class, you have learned that the derivative of du over u, or sorry, the integral of du over u, is the natural log of u. Sound like something familiar, I hope? And because these are both indefinite integrals, I have added a constant to each side. I've called this one C1 and this one C2. Okay, so I've taken an integral of each side. Now we have this nasty natural log in here. All right, this would be a lot easier to do if this wasn't a linear if this wasn't a first order separable differential equation, but it is what it is. And this is the one that tends to show up on the AP test more often than not. So first thing I'm going to do here then is I'm going to combine the two constants together. So I'm just going to call our new constant C. Okay, nothing else has changed. Now, remember that we're trying to find, keep this in mind, a velocity function. Velocity is a function of time. Well, we now have time in the equation, so that's good. But if you remember, the velocity is hidden inside of the u, right? FO minus KV, right, is u. And I don't want to know the natural log of this. I want to know, the velocity. I want to be able to solve for the velocity. So we got to do something a little tricky here. If we want to eliminate the natural log, we have to do this. We're going to say e to each side. So this is e to the natural log of u, and this is e to the negative k over n times t plus c. Fancy math. It's a process, folks. Hopefully you recognize that e to the natural log of u is simply u. Over here, I'm going to kind of do this in a little different way than kind of the opposite way you do most things in class. Instead of combining together two terms, I'm actually going to separate this into two terms. Right? We're adding two exponents together. Isn't that the same as multiplying like this, right? E to the c times e to the negative k over m times t is this, right? Because they're added together up here. And e to the c is just a constant. And so to make our life easy, I'm going to call e to the c a constant of c. And then I'm going to plug in for u f of o minus kv. Now we have an equation. It's not a nice one, but we have an equation we can solve for v. The only other variable is t. So, some algebra. We get velocity is equal to f of o minus c times e to the negative k over m times t, all over k. But I can't use this constant in here. That's not one of the allowed variables. But we do have an initial condition we can apply, which is that the car starts from rest. So at 0 time, right, the velocity is 0. Let's plug that into the equation. Here it is. Well, 0 times anything is 0. E to the 0 is 1. If we multiply the k over to here, it cancels out. And so we end up with c is equal to f sub o. Check out the algebra there. I did several steps, right? You can eliminate the k because you can multiply it over here. E to the 0 is 1. So that's 0 equals f of o minus c, and solve. So we plug this in for our constant, and we actually have the equation. If you want to, you can factor out f of o over k. Right? And this is the answer they're looking for. If you left it this way, by the way, they'd be perfectly happy. You'd get full credit. Now, I'm going to go over this again quickly, but that is a lot of calc. Right? This would take a while on a test, but it is what it is. It is a pattern. And on the worksheet that's associated with this, you have several other examples that you can do. So, we took the equation. We turned it into a differential equation by plugging in for the acceleration dv over dt. We then separated the variables, did a little u substitution, substituted that in to make a simpler equation. Unfortunately, when we simplified it, we got 1 over u du as an integral, which threw in a natural log. Right? We combined the constants together. We said e to both sides in order to eliminate the natural log, because e to the natural log of u is simply u. We broke this down into two terms, gave the constant a new name, plugged back in for our u that we did the u substitution with, and solved for v. Put in our initial condition, figured out our constant, and there's our equation. It's not nice, it's not pretty, but there it is. So let's go on to the rest of the problem. So the next part they wanted you to do is they wanted you to make a graph of this function. It's kind of interesting that with the last couple of parts to this problem, you actually could probably get some of these points even if you had not been able to actually derive the equation, if you just thought your way through it. Right? I mean, let's think about what's going to happen here. All right? This car is going to get moving, and it's going to speed up because of that force F of O, right, acting on it. But as it speeds up, the resistance force is going to increase because the resistance force is negative kV. Right? So as V increases, the resistance force increases. Well, as the resistance force increases, the net force, the difference between F of O and the resistance force, gets smaller. And as the net force gets smaller, the acceleration gets smaller. And that means the car continues to speed up, but it speeds up more slowly. Until some time in which those two forces would be equal to one another, but we'll get to there in a moment. Okay? So on our graph of velocity versus time, the slope of which is the acceleration, right? We're going to have a big slope to start out with, steep slope to start out with, right? And then, and by the way, it's going to be positive because the net force will be positive, so a steep positive slope. And then as time goes on and the resistance force builds, so the net force decreases, so the acceleration decreases, the slope of this graph is going to get less steep. Can you visualize what that's going to look at? You actually can get a point just by thinking through and drawing that shape of the graph. Now, the other point you're going to get here is for labeling important values. There's an asymptote on this function. And I know I always say that weirdly, but deal with it, people. And we need to figure out where that is. And we can do that by looking at this function and evaluating it as the time approaches infinity. Okay? So as time approaches infinity, what's going to happen to this function? Well, we've got this weird exponential thing going on here. So notice that it's negative, though. So this is really like 1 over e to the k over m times t, and k and m are constants. Right? So as t gets bigger and bigger, 1 over this is going to get smaller and smaller. And when t approaches infinity, this will approach 0. Right? Remember, this is 1 over this, really, to get rid of that negative sign. So as t gets bigger and bigger, right, this gets bigger and bigger, which 1 over gets smaller and smaller. So it approaches 0. And when it does that, and this becomes 0, note what we have left. Right? The velocity will be F of O over k. So if I put that in, our function is going to look like that. Steep positive acceleration to start out with, large positive acceleration to start out with, and then getting less steep, which means a smaller positive acceleration. It's still speeding up, but it's speeding up more slowly. And it will continue to do that, right, getting closer and closer to F of O over k. So note, you could get a point if you just graph that shape. Second point, you needed to apply infinity to time to figure out the asymptote. So now they want a graph of the car's acceleration as a function of time. And they want you to label important values on the vertical axis. Well, we've got the acceleration function already, but it's the acceleration as a function of velocity. So how are we going to get the acceleration as a function of time? Two ways. Oh, by the way, at t equals 0, right, the velocity is 0. Right, so if the velocity is 0 at t equals 0, so that means the acceleration at 0 is f of o over m. So that's where the acceleration is going to start. Now, as time goes on, what happens to the acceleration? Right? Well, the acceleration is going to get smaller and smaller, as we talked about before, because the resistance force gets bigger, so the net force gets smaller, so the acceleration gets smaller. Right? So if you sketch in a curve here, right, you actually could finish this and not have to do any math at all. They didn't ask you to derive the equation, right, or anything. They didn't even ask you to justify your answer. So if you just drew a curve, getting less and less steep, starting at f of o over m, right, you'd be done. A couple of points, I believe. But since we're here, I'm going to show you the math. Two ways to do the math. One is the acceleration is the derivative of the velocity with respect to time. So if we plug in our velocity function, right, this is the function we found in the earlier part, and we take the derivative of this function with respect to time, we'll get something like that. Please remember that the derivative of an exponential is the constant, times the exponential back again. So notice the negative here and the negative here cancel out. That's why this is positive k over m. By the way, the derivative of 1 is 0, right? So that part drops away. You do the derivative of a difference is the difference of the derivatives. And so this is what we get back. Hope you're okay with that little derivative of an exponential. All right, and the k's cancel. And so there's our acceleration function. Note, when t is 0, e to the 0 is 1, and the acceleration is f of o over m, like I showed you earlier. Method 2 actually doesn't require any calculus. We've already got the velocity function. We've also got the acceleration as a function of velocity. Substitute. You've now eliminated velocity and entered the time as a factor. And now we just need to do some algebra. The k's cancel. We get this thing. Notice when we put this negative through, f of o minus f of o is 0. And so we're left with the function that we got before. This negative and this negative cancel out, right? So we get this. Look, this is not easy. All right, not easy in any way, shape, or form. All right, it's actually something called differential equations. It's the simplest, if you can believe it, type of equation to solve that you learn in differential equations. But again, it shows up about every 3 years. If it pops up, maybe you've got a fighting chance to work your way through it. But another thing to pick up from our treatment of this problem is that there were points that you could get along the way. By the way, in 1993, you could get 7 points on this problem by doing the force diagram and by finding the acceleration, right? Which, if you remember, those were pretty simple, right? That's parts A and B. The average on this question in 1993 was like 7.1 or something. So almost nobody got any points after B. They just kind of went on from there. But I do this at the very end of the year in case it shows up on the test. You've got at least a fighting chance to work your way through the calculus. So I would then suggest here that you do the worksheet and check out the key for the worksheet and work through some problems. They are all old AP problems in which this method needs to be employed. They are all where you have resistive forces as functions of velocity. Right, so t equals 0, a equals f of o over m. As t approaches infinity, right, a approaches 0. Here's our function again, right? And so it would look like that. Okay, so there's our equation. Again, you might be able to think your way through this without doing any calculus.